Hi, welcome back. With a bunch of optimization tools and statistical learning tools have been discussed. So now, before proceeding to classification models, just to avoid monotonicity, so let's talk about another grouping technique where the data does not come with labels. Okay, so this can always happen. I mean, gene microarray expressions, and large catalog data, right? Like one example that I can give you is that, I mean, there is this catalog known as GALEX, I mean, which is Galaxy Evolution Explorer, is a NASA mission in 2012. I mean, it was shut down in 2012, and that particular catalog has approximately 10,500 samples with stars, quasars, and galaxies. Okay, so there are some of these are galactic objects, some of these are extragalactic objects, and the idea is to be able to automatically classify this. Okay, so the problem is that, and we do have some information, both spectrometric and photometric information, but the problem is with the Chinese mission and the Russian mission, the data has been accumulated in a very large amount, and most of the data, unfortunately for us, do not have labels. So we have about 10,500 samples with labels, and we have about 1 million samples which do not have labels, right? And if you also look at the geometric distribution, I mean, you are probably not able to find sort of a hard marker between the classes, so that you can say, okay, this particular data grouping is belonging to this class, this particular data belongs to this class, and blah blah blah. Okay, all right. So the obvious advantage. So what would be a remedy to such a problem? So you can think about doing this. Let's pick up one data point, okay, and let's start with random initialization of a bunch of groups or clusters. Okay, just some random. So let's say we start with k clusters. And let's pick a point, okay, and that's a test point, right? Okay, and let's pick some other points and compute the distance of the test point to one particular cluster, compute the distance of the test point to other clusters as well. Okay, assign the cluster, assign the point, assign that particular data point to the cluster where the distance is the minimum. Okay, and do that across all points, and as and when points come in, you determine based on proximity of that particular data point that which cluster or group this data should belong to. Now note one thing here is that we do this, it's a deterministic method. Okay, so we are completely ignoring the possibility that there could be a differential grouping or like a preferential grouping of a data point, right? I mean, in the sense that, I mean, a data point with certain probability can belong to one cluster, with a certain probability it can belong to another cluster, with certain other probability it can belong to another cluster if there exist multiple clusters. Okay, we completely ignore that possibility and we hard assign a data point to a cluster. Okay, all right. So what we do is, I mean, if you look at this particular image, right, I mean, there are data points which are sort of distributed in many weird different manner, right, and you can see one particular model where you can see a Gaussian mixture model where you have the orange and the blue lines, right? I mean, so this does a very pretty good job. This one, DBSCAN, which is a density based clustering algorithm and not based on geometry, this does a very decent job where you see absolutely no overlap between the orange and the blue ones, right? Okay, so this is a clustering. So what it means is that, I mean, I have a point. How do I assign a point to a group? So let's choose a point somewhere over here, right? Okay, let's choose a point somewhere over here, compute the distance of the point from this cluster, and then compare the distances. The one with the minimum distance is the candidate cluster for that particular point. So it's like this. I mean, I have bunch of clusters. Let's say I have k clusters, and each cluster is bidding for one point, okay, to belong to itself, right? The bid depends on the distance of the cluster and that point itself. So lower the distance, greater is the bid. So it's like a sort of inversely proportional thing, right? Okay, all right. So the question is, what is the concept of this clustering? And then the next question that pops up is that how many clusters, okay, do we have? How many clusters do we have? So, and then what is a good enough measure of clustering? I mean, there are a bunch of things that we can, So let's sort of think about clustering technique, which is also known as k-means. Okay. All right. So k-means is a very popular clustering algorithm. It's pretty simple. Okay. It's pretty simple. And it's an iterative process where you update the data points to clusters and update the cluster summarization as well. Okay. And we begin by assuming that there are k clusters. Since there are k clusters, for each cluster you compute a mean, right? And therefore you compute there are k means. So you represent each cluster by its location. Okay. And suppose an example data point has bunch of features, right? So we represent the assignment of the example, and then we have a distance function which we want to minimize, and the distance function depends on the distance of that point, right? Okay, and the mean of the cluster. So I mean, of course, I mean, if as I was saying right earlier, you have to compute the distance between a cluster and a point. How are you going to compute the distance between a cluster? You're going to compute the distance between the mean of the cluster and the point. So this is like a geometry based. Okay. All right. So for each data point, you try to find the closest cluster. Okay. So, and then what you do is set each cluster to the mean of all assigned data, right? You compute that, and you will find that, what you find is actually not surprising. You will find that the mean is actually at around the center, okay, which is exactly, and then the other thing is probably what you try to do is there is a cost, right? There is a cost of assigning, there is a reward. There is no reward of assigning a particular data point to a cluster, but there is a cost of, not being able to assign a data point correctly to a cluster. Okay. All right. So the idea is to minimize the cost. I mean, if you are able to minimize the cost, you probably have assigned data points to the appropriate clusters. Okay. All right. So what we do is we do a descent technique, right? I mean, and therefore, I mean, just like any gradient descent technique, if you recall the gradient descent technique, right, it has a local oscillation problem or a local minima problem. Okay. All right. And then you have to also compute many heuristics, like for example, how do I initialize the cluster? So we typically, use random heuristics as in, start randomly, I mean, assign k clusters and their means randomly, right? Okay. And also the question is, what is the optimal value of the k? How many clusters should I choose? Okay. All right. Okay. So these are some of the issues of, k-means clustering. And, basically what it does is, what k-means does, it assigns one data point to exactly one cluster. So there is no notion of a probabilistic belongingness. Okay. All right. And also the other problem is this. The other problem with k-means is this. Now see, let's look at this particular example, right? I mean, typically what happens is k-means does a pretty good job if your clusters are non-overlapping. Right? I mean, if you have one cluster somewhere over here, and one cluster geometrically away from the other cluster and blah, blah, blah. Right? So, I mean, as long as the geometric separation is evident, k-means does a decent job. But in this particular case, what you see here is that you have data points which sort of is elongated, right? I mean, along an ellipse, and then you have data points which belong in an ellipse. Now, what k-means will do is that, I mean, it will wrongly assign data points to clusters, okay, because these are overlapping. Okay, so I mean, also it's a sort of I mean, let's pinpoint on this guy, right? What do you say? Which cluster does this guy belong to? We don't know, right? I mean, it's hard to say, and therefore it's important to bring in this notion of probabilistic belongingness, which is get a point and see what is the probability of this particular point belonging to this particular cluster, the longer ellipse, and this probability of belongingness of this point to the other ellipse. Okay. All right. Not just based on their mean. Okay. So this is what, I mean, this is where the Gaussian mixture model comes in, and this is where we say that k-means is actually a special case of a Gaussian mixture model. Okay. All right. So where you are modeling the clusters as Gaussians, and not simply by their mean. Okay, and then you also assign some sort of a probability. Okay, but before I go to the Gaussian mixture model and the expectation maximization method, we would like to know a little bit about k-means itself. Okay, all right. So let's do some calculations, and let's talk about k-means in a little more detail. Okay, so this is what I have. I have data. Okay, so one dimensional representation. Okay, all right. Now the thing is, you don't see any levels. There are no y values. I don't know the y values at all. So unlike regression where you have ordered pair information x1, y1, x2, y2, xn, yn, blah blah blah, here you don't see any y value. Okay, so typically the ideal situation is like this. I have some data points here. I have some data points here, right? And I have some data points here. Okay, so what we do is we sort of intuitively or visually speaking, we say, okay, these three seems to be good enough. I mean, right? I mean these data points seem to belong to this cluster, these data points seem to belong to this cluster, and these data points seem to belong to this cluster. Why? For the simple reason, and that you pick a point here, right? You pick any point here, okay, and then you find its neighbors, right? I mean, let's say you have some neighbors here. You compute the distances, right? Okay, basically the Euclidean distance, and then you pick some other guy over here, which belongs to another cluster, as you can see. Compute the distance of this data point to that, right? Okay, or rather, actually, what you do is you pick the mean of that cluster, right? You compute the distance of this mean, compute the distance of the data point from that mean, and you can see that obviously the distance between this point and the mean of the other cluster is much greater than the distance of this point and the mean of the cluster it belongs to, and that is how you decide the assignment of the clusters. However, this process is heavily dependent upon the fact that your data distribution is sort of spherical. Okay, spherical meaning the variance and the covariances are constant. Okay, all right. I mean, which is a key thing that we assume in k-means. Okay, all right. So to begin with, we assume k clusters, and each cluster has a mean. So there are k-means. Okay, all right. Now, actually, we really don't know where the centers of these clusters are, right? So let's say I take one cluster. Let's call this cluster 1, and I have these means, right? These are the means, right? Okay, and I try to compute the distance of a data point from the mean, right? And I call this some value L. Okay, all right. So what has happened is this is assigned to, this means that this is assigned to the jth cluster, if it is, right? And j can be 1 to k, right? Okay, and then what I also do is we sum over all clusters. This is the distance that we need to minimize, right? Because I'm assigned one data point to a j cluster, then a j, we have bunch of clusters, right? We have j clusters. So and then take the sum of all of that. And that sum, this whole thing has to be minimized in order to determine whether xi is an appropriate belongingness, enjoys appropriate belongingness to cluster j. That's exactly what we want to. Okay, all right. So in other words, I mean, I can rewrite this by bringing in a characteristic function. So let's rewrite this with j summing over all clusters and I summing over all data points, right? And bringing in a characteristic variable. Okay, all right. So the goal is to minimize. Okay, all right. Now let's talk about this guy. This is a characteristic function, right? So characteristic function means it can have a value 0, it can have a value 1. When does it have 0? I mean, what does it imply? Right? I mean, if the value of this guy is 0, that means the data point I does not belong to the cluster J. If the value of this guy is 1, that means the data point I belongs to the cluster J. So it's like a smart trick. Okay. All right. So the idea is, the problem is to minimize L with respect to A and mu. Okay. All right. So so how do we do this? We choose an optimal A. We choose an optimal A by fixing mu, and then choose an optimal mu for fixed A. And we also have to initialize all mu's, right? Mu1 through mu k. Okay. All right. And typically, usually what we do, this is arbitrary. Okay. And we repeat until convergence. Okay. Well, I mean, I'm not going to compute the first derivative, but I'm just going to show you that this is a solution to the optimization problem is nothing but, I mean, what you do is you compute the partial derivative, right? Okay, because you have bunch of clusters, J clusters, right? And when you do that, basically, because it's a multivariate function, this is what you have to do, right? And this is what you want. This is what we want. Okay, if we do this, I mean, I'm going to skip the pretty straightforward, vector differentiation. What you are going to get is this, and this is important, and let's focus on this. Okay. So this is what is your critical point. You know, in a maximization or optimization problem, you have a critical point, and then you test whether the critical point gives you a, minima or a maxima based on your, sign of the second derivative, right? Okay. So, but what you see here is that this is, what is this? This Aij is the characteristic variable, right? Okay. And this Aij is 1 when the cluster is appropriately, the data point is appropriately assigned to a cluster, right? Okay. So it's a convex combination of all the data points that we have. Xij's are the data points. Okay. So it's like a mean. It's like a sample mean. I mean, you have a bunch of data points and you have a sample mean, right? It's sort of samples are weighted by their characteristic function. Okay. Now, if I compute this second derivative, which is assuming that this is the critical point, okay, then the second derivative is nothing but times the identity matrix. Okay. All right. Now, what does this mean? We know that these Aij's are 1 and 0s, right? I mean, so it's like there is no way the second derivative can be negative, right? Okay. All right. And so this is greater than 0. And what this means is the Hessian, this is called the Hessian. The Hessian is positive definite, which means that you have a minima. The minima is guaranteed. Okay. All right. So we repeatedly do this and we find out the distances between the data points and their respective cluster means, and we say that the convergence is sort of guaranteed because we have a minima. Okay. All right. Okay. Now let's say Nj is nothing but, just set this. Okay. All right. Which is actually number of points. Okay. And xi assigned to j. Okay. Now this is positive definite as long as xi is, as long as Nj is assigned to mu j. Note this. Okay. Okay, so therefore, the estimate that we have over here, okay, it says sum of all the points xi assigned to the cluster J. Okay, so the only problem, so basically I can rewrite this as mu j equal to 1 over nj. Okay, so this is nothing but the, as I said earlier, this is nothing but the empirical mean of the data points, okay, around the clusters. So I mean, can you tell me what's the problem with this particular representation? The problem with this particular representation is what happens when nj equal to 0. So this assignment becomes invalid, right? I mean, when nj is equal to 0, I mean, which is the number of data points is like 0, right? I mean, then this assignment becomes invalid. So what we will do is to restart the algorithm. Okay. However, I mean, at least I haven't seen this to happen. At least when I try to do k-means clustering. Okay. However, one thing that you see in this discussion and conversation, that I mean, the assignment of points to clusters is hard. Okay, so the allocation of, this is one of the drawbacks of k-means. This will actually lead us to more general strategic clustering methods. Like I'll give you an example. Like let's say we have, now I mean, if I give this data to k-means, what do you think it will do? What will try to do is, I mean, it will, let's say there is a point over here and then there is a point over here, right? Okay, so I mean, since it sort of tries to find, I mean, it will randomly have like bunch of, it'll try to create, let's say, some bunch of clusters, right? Okay, bunch of clusters. So what it will do is, I mean, the problem is, I mean, as long as it creates clusters like this, we still no problem. But what it will try to do is, since these 2 points are geometrically close to each other, okay, what it can potentially do is sort of pick a cluster like this. Okay, all right, based on the fact that both of these points are close enough to the mean of the cluster compared to the other points. But ideally speaking, that's a wrong assignment. This is wrong. And the reason why this is wrong is because k-means picks data based on their geometrical distribution in space rather than based on density. Okay, so this is one of the problems that k-mean faces, and there are some other algorithms, there are other clustering methods that are used to mitigate this kind of a problem. Okay, so k-means is not at all density based, so it's not density based. Okay, so what do we do in order to sort of avoid this kind of a situation? Okay, so I mean, probably some remarks I would like to make at this point of time is that, so which means expectation maximization, or EM, is a more general method which comes from a Gaussian mixture model, right? Okay, and what happens in k-means is that there are like, it deals with spherical clusters, right? Which means the variances and covariance matrices, I mean, they are identical covariance. And because it's like a sort of suited for spherical clustering, k-means intrinsically assume that clusters are grouped around circles, right? I mean, much or less round. Okay, all right, so it's not heavily elongated, like it's not stretched like an ellipse and stuff like that. Okay, and so what EM does is, unlike k-means, I mean, what EM does is it's actually works on a soft assignment okay, sort of a probabilistic, okay, all right. So the expectation that your data point is in a cluster is based on a probability, okay. So the expectation that, okay, so let's continue at this in the next lecture, okay, I mean where we talk more about the expectation maximization and the Gaussian mixture model, and also see how these models evolve based on very complex allocation of data points, okay.